Okay, so today I'm going to present a topic called inference acceleration for large language models using stairs-assisted tree generation. Um, I'll try to explain what does it mean in several steps. So at the beginning, what we're talking about was the objective, was the problem, then some inspiration, really short, maybe 2 minutes of trying to get up to speed of how the LLMs are predicting next tokens, then another 2 minutes what we are doing, and finally some experiments, results, and everything like that. Without further ado, let's begin. So the problem is that if we have large language models, let's say with billions of parameters, they know that they are impressive. We saw GPT-4o, for example, just recently released. It's pretty cool. But one thing is that they're actually pretty slow to generate new tokens. So if you ever try to run model on your computer or something, you probably note the larger the model, the slower it is. On the other hand, if we have smaller models, let's say with million parameters, they are faster, but they're less accurate. So what about if we combine those strengths and come up with something cool? So essentially the objective is the accelerate inference, which is just simply you give something and you get back from it, from the main model, the larger one, by using smaller models help. And the cool bit is that we are not altering like model architectures, some training procedures, like we don't need to retrain models or have some adjustments with the hardware. So it's kind of can work with multiple architectures, multiple models, and that kind of stuff. So some inspiration, really briefly, it's kind of a newer concept, but tackled from different companies in different areas. Yeah, even some context you can find on the Twitter, which is actually very relevant. So without further ado, so very first bit that I want to talk about is how the regular generation works. It really abstracts view in terms. We can see that, for example, we have input my dog is. We put it to a large language model plus the context that we have a prompt. It does the magic, comes up with the next possible best option. So in this case, we have nice, happy, and cute. It gives us some score, and because we have this greedy case, which is pick the highest score. So in this case, it's cute, and the output is my dog is cute. Hope this is easy. Now you close your eyes and open again. Oh, it's a larger example, but in this case, it's exactly the same as I saw before, just more steps. So we begin as an input my, and we see that the dog is the best second option. We get the output. We use the last bit of the output or the second iteration, my dog. We get the result my dog is. We use that, and finally we get my dog is cute. The important bit here to notice is that for the model, it took 3 iterations to achieve this result. For this specific example. Now we go deeper. Here is again, very abstracted version of how assisted generation works. So we have the same input as we begin, like my, we put it to assistant model, well, and we do exactly the same steps I just showed you in the previous slide, just to the smaller model. It gives us some kind of a result. In this case, it's barely visible, but it's written that my dog is nice is the provided answer. What we do with that, we give it to the large model, and now we have some assistants that are happening, and we're checking each token one by one. Is it really what would the large model would have predicted? So we see that, for example, my dog makes sense, my dog makes sense, my dog is nice. Well, actually, that's not what the big model would predict, as you saw in the previous slide. So now we only take the part that was correct, my dog is. We actually do the prediction with the main model. We can have the same case where we pick cute, and at the end we have my dog is cute. More complexity here. So what we actually proposed is a slight modification of assisted tree generation, where we also have the same input. We have assistant model, we have assistant model output, and then we put it into this stairs batch, which nicely cascades, adding where every line has one more token than previous line. What we do, we give this batch to our large model. There's a cool trick that actually, if you give a model, a really large model, the batch prediction or just a single prompt, there is difference in performance, but it's really negligible, small difference. Essentially, if you would have 4 different prompts versus the batch prompt is way more efficient. So what we do, we give this batch. We do predictions for each of them, one token. And then we do this validation outside the model. What we do, we check, example would be, we check in the first line, we have predicted that the dog is going to be a response. We know that it's true because the main model predicted it with true input. Now we use, in the second line, we use my dog and have this new token is. We compare it with the third line, third token. In this case, it's correct, it matches. So we now know that my dog is correct prediction. And now we have third line for token Q. We compare it with the fourth line for token, which is nice. We know that that's not correct, like it doesn't match. So we stop there, we don't go any further. If we have anything, we just go proceed with my dog is cute. And essentially, that's the final output. If that would be the final generation, we continue the loop again, but in this case, that's the end. So cool, enough about the talk. Let's talk about experiments and results. So what we did, we had two main models, essentially two benchmarks to look for. One was using a encoder-based model of T5 large, and the second was T5 3 billion, respectively with their parameters. And we used a smaller assisted model, essentially T5 small, which had only 60 million parameters. We ran it on the MacBook and with this single prompt, translate English to German, my dog is cute. So we had two experiments. So one experiment was to determine best batch size. So essentially how big, how say long or batch or prediction we want to have when we try to run, let's say those predictions. And the second, the main one was actually comparison. What we did, we took the original model without any modifications. Then we had Hugging Face assisted generation implementation and our proposed implementation and see what were the results. So as we can see, we began with T5 large model, and on the left side, on the left-hand side, corner side, you can see the batch size comparison. So it actually turns out it matters, which kind of makes sense how much into the future you want to predict. And in this case, we had that the best prediction, the fastest prediction was with the prediction 7 tokens into the future with a smaller model. We'll use that in our benchmark against other models. So on the right side, you can see the graph of comparison with other models. You can see the plotted how much time does it take to predict our sentence on the Mac that I talked before. And the first one is the original model. Second one is Hugging Face assisted generation. The third one is our generation. So we run 1,000 runs for each of experiments, and you can see this distribution plotted in this graph. And we can see that Hugging Face assisted generation was roughly around 6% faster compared to just single model. Our implementation was around 17.2% faster compared to original model. Of course, you can see the distributions are scattered. That could be a nice experiment to figure out why and essentially why. Another experiment with a bigger model. Again, we did some batch size comparisons, saw some similar trends. And on the right side, the more important bit is about the comparison of essentially the biggest model, the big models, right? So T5 3 billion. So we see original takes around 1.2 seconds to be predicted. Hugging Face assisted implementation trimmed that down to 0.95 seconds, or roughly 22% faster. And our implementation did that in around 9.5% faster compared to the original single model implementation. So we kind of came to the conclusion that this assisted video generation indicates potential to be faster inference protocol versus just standalone model. And even in some cases, it managed to beat the Hugging Face implementation, which I find pretty cool. And yeah, for the future, there were a lot of ideas that could be done, starting from just using more data. It was very simple prompt at the beginning. We used regeneration. For example, if you would use sampling, we would block a temperature parameter. We have some variation. That could be also interesting. Different size assistant models, we don't know, maybe it would perform better. And also different type of assistant models. Now we just reuse the same architecture, or the smallest version possible. What about if you use the same architecture but different model? Maybe we have some different results. And with that being said, I'm finished. So thanks for your attention.